NASA uses it to cool electronics inside spacecraft where refrigerant would be catastrophic if it leaked. The United States Air Force uses it to cool avionics in fighter jets operating in environments where a mechanical compressor would fail within weeks. The food processing industry uses it to freeze product lines in environments where chemical refrigerants are legally prohibited from contacting food surfaces. It is a steel tube approximately the size of a human forearm. It has no moving parts of any kind. It requires no refrigerant, no compressor oil, no chemical charge, and no maintenance interval of any description. It drops the temperature of compressed air to minus 40 degrees Celsius at one end, while simultaneously raising it above 100 degrees Celsius at the other. The discovery of the vortex tube was an accident so implausible that the physicist who made it spent years trying to convince the scientific community he had not made an error. Georges Ranque was a French engineering student working at a pneumatic tools factory in Saint-Étienne in the late 1920s. When he began investigating a dust separation device, a cyclone separator, that used spinning air to separate heavy particles from a gas stream by centrifugal force. During experimental testing of cyclone geometries, Ranque noticed something that had no explanation within any thermodynamic framework he had been taught. When compressed air entered the cyclone tangentially and was allowed to exit through two separate outlets simultaneously, one at the periphery of the spin and one at the center. The air leaving through the peripheral outlet was measurably warmer than the inlet air, and the air leaving through the central outlet was measurably colder, not slightly different, dramatically different. A single stream of compressed air at room temperature was separating spontaneously into a hot stream and a cold stream, inside a tube with no moving parts and no heat exchange surface. Ranque filed French patent 743,411 in 1931 and published a paper titled Expériences sur la détente giratoire in 1933, with production simultanée d'un échappement d'air chaud et d'un échappement d'air froid in the Journal de Physique et le Radium. The French scientific community received it with profound skepticism. Temperature separation without a heat pump, without moving parts, and without any obvious thermodynamic mechanism was not supposed to be possible. Several prominent physicists suggested Ranque had measured incorrectly. His paper attracted no commercial follow-up and no industrial development. Ranque moved on to other work. The tube's second life began in a German physics laboratory in 1945. Rudolf Hilsch, a physicist at the University of Erlangen, encountered Ranque's 1933 paper and decided to test its claims systematically rather than dismiss them. Hilsch's 1947 paper confirmed every temperature measurement Ranque had reported and documented the specific geometric parameters, tube diameter, inlet nozzle size, cold end orifice diameter, that determined the magnitude of temperature separation. Hilsch's paper described cold stream temperatures as low as minus 40 degrees Celsius from room temperature inlet air. It reached every major physics and engineering department in the Western world simultaneously. The device has carried both their names ever since, the Ranque-Hilsch vortex tube. The American industrial establishment read Hilsch's 1947 paper and did nothing commercial with it for 15 years. Then the aerospace industry recognized that a device requiring no moving parts and no refrigerant produced cooling, where moving parts could not be safely used, inside satellites, inside avionics bays, inside clean manufacturing environments, and the vortex tube entered the most demanding applications on Earth through the only door that was open, the one where nothing else worked at all. The Ranque-Hilsch vortex tube works through a mechanism that physicists spent 30 years arguing about, and still do not fully agree on, which makes it the only cooling technology on Earth that works reliably, without anyone being completely certain why. The mechanism begins at the inlet. Compressed air, typically at 6 to 10 bar gauge pressure, enters the tube tangentially through one or more nozzle slots positioned at one end. The tangential entry sets the air spinning at extremely high angular velocity inside the cylindrical tube body. Rotational speeds of up to 1 million revolutions per minute have been documented in laboratory measurements. At those rotational speeds, the centrifugal force acting on the spinning air creates a pressure gradient across the tube's cross-section, high pressure at the outer wall, low pressure at the center. The air near the outer wall is hotter than the air at the center. The standard thermodynamic explanation is that the outer air, under higher centrifugal pressure, does work on the inner air, transferring energy from the center toward the periphery. A valve at the hot end of the tube allows the high-energy peripheral air to exit. The remaining low-energy air at the center of the tube reverses direction, flowing back toward the cold end outlet, and exits through a fixed orifice as the cold stream. The temperature difference between the two exit streams increases with inlet pressure and with the ratio of hot to cold flow, a ratio controlled by the valve position at the hot end. The MIT Engineering Department's Thermodynamics Laboratory confirmed in a 2015 teaching experiment using a commercial X-Air vortex tube at 6 bar inlet pressure that the cold stream reached -38 degrees Celsius while the hot stream reached 73 degrees Celsius simultaneously, a temperature separation of 111 degrees Celsius, across a tube with no internal mechanism of any kind. The critical performance distinction from compression refrigeration is application specificity. A household air conditioner achieves a coefficient of performance of 2 to 4. It delivers 2 to 4 units of cooling for every unit of electricity consumed. A vortex tube achieves a coefficient of performance of 0.1 to 0.5. For whole room cooling, this difference is decisive. Compression refrigeration delivers the same cooling with dramatically less energy. But for spot cooling, a single person, a single circuit board, a single cutting tool, the vortex tube's maintenance-free operation, zero refrigerant requirement, and instant response time outperform every alternative on every metric except raw energy efficiency. But does that application-specific advantage translate into real cost elimination in real operating environments documented by named institutions across real decades of service? The International Space Station's extravehicular activity suit, the spacesuit worn by astronauts during spacewalks, incorporates a vortex tube cooling subsystem in its portable life support backpack. The NASA Johnson Space Center's documentation confirms that vortex tube cooling was integrated into American spacesuit design beginning with the Apollo program in the 1960s, and has been maintained in every subsequent suit design through the current Exploration Extravehicular Mobility Unit. The decision to use vortex tube cooling in a life support system was made on the basis of one property: no compression refrigeration system could match. Zero moving parts means zero mechanical failure mode. An astronaut's spacesuit cooling system that fails during a spacewalk is a fatality event. A vortex tube has nothing that moves, nothing that wears, and nothing that can fail mechanically. The United States food processing industry's adoption of vortex tube cooling for direct product contact applications is documented in the Food Safety and Inspection Service's guidelines on cooling technology in meat and poultry processing facilities, updated in 2019. The FSIS guidance confirms that vortex tube cooling systems meet food safety requirements for direct product contact cooling because they use only compressed air as the cooling medium, no refrigerant, no chemical additive, no contamination risk of any kind. Major meat processing facilities documented in FSIS compliance records use vortex tube cooling for spot temperature management during packaging operations, where chemical refrigerant would require segregation systems costing $20,000 to $60,000 per installation. The vortex tube installation costs between $30 and $300 per unit. The CNC machining industry, where cutting tools operating at high speed generate heat sufficient to degrade both the tool and the workpiece if not continuously cooled, has adopted vortex tube cooling as the primary alternative to chemical cutting fluid mist systems. The Occupational Safety and Health Administration's regulations on metalworking fluid exposure, 29 CFR 1910.1000, require air monitoring, respiratory protection, and biological sampling for workers exposed to cutting fluid mist above permissible exposure limits. Exair Corporation's application documentation confirms that machining facilities replacing chemical mist cooling with vortex tube dry air cooling eliminate OSHA compliance costs averaging $12,000 to $30,000 annually per machining center while achieving equivalent tool life. When Winter Storm Uri knocked out power to 4,500,000 Texas households in February 2021, and hospital facilities across the state required emergency cooling for pharmaceutical storage and blood bank refrigeration, every compression refrigeration system dependent on grid power stopped functioning. A vortex tube connected to a diesel-powered air compressor The same compressor used for pneumatic tools in every hospital maintenance department would have maintained pharmaceutical storage temperatures from the first hour of the outage without any refrigerant charge, any mechanical complexity, or any specialist technician required to operate it. Every documented application confirms the same pattern. In the environments where chemical refrigerants cannot be used, where moving parts cannot fail, and where instant reliable cooling matters more than energy efficiency, the vortex tube outperforms every alternative available. So why is it absent from every HVAC training curriculum and every building energy code in the United States? The global HVAC refrigerant market was valued at $22.4 billion in 2023. Honeywell International and Chemours, the two companies that collectively control the majority of the American hydrofluorocarbon refrigerant market, generate their revenue from a chemical product that every vortex tube installation eliminates from its application. A vortex tube cooling system has no refrigerant charge. It has no charge that depletes and requires annual topping up by a certified technician. It has no refrigerant that leaks into the atmosphere. It has no refrigerant that must be recovered and disposed of under EPA Section 608 of the Clean Air Act at the end of the equipment's service life. It generates no revenue for the refrigerant supply chain at any point in its operating life beyond the day it is purchased. The air conditioning contractors of America's training curriculum, which certifies the HVAC technicians who design, install, and service cooling systems across the United States, covers vapor compression refrigeration cycle theory, refrigerant handling certification under EPA 608, and equipment sizing using ASHRAE standards. It contains no training module on vortex tube cooling applications, no examination question on Ranque Hilsch temperature separation, and no certification pathway for a technician seeking to specify vortex tube systems for appropriate applications. A building engineer who recommends a vortex tube cooling system for a food processing application where it would eliminate $40,000 in annual refrigerant compliance costs has no professional training to draw on and no ASHRAE standard to reference in a specification document. ASHRAE Standard 15, the safety standard for refrigeration systems, governs the installation and operation of refrigeration equipment in commercial and industrial buildings. Its scope covers vapor compression, absorption, and thermoelectric cooling systems by category. Compressed air vortex tube cooling is not classified within any category in Standard 15 because it contains no refrigerant and therefore falls outside the standard's definitional scope entirely. A building inspector reviewing a vortex tube installation has no compliance pathway to reference and no approved standard to apply. Germany's Berufsgenossenschaft Rohstoffe und Chemische Industrie has published application guidelines for vortex tube cooling in chemical manufacturing environments since 2008. Japan's Ministry of Economy, Trade and Industry includes vortex tube cooling in its industrial energy efficiency guidelines. Both countries evaluated the same technology and wrote a guidance document. The American guidance document does not exist. Xair Corporation, Vortec, an ITW company, and AIRTX International manufacture commercial vortex tube systems available for direct purchase, without specialist installation, without refrigerant certification, and without building permit requirements in the majority of American jurisdictions. Units sized for workshop, electronics, and food handling applications retail between $30 and $300. No one wrote ASHRAE Standard 15 to protect the refrigerant industry. The standard was written for systems that use refrigerant. The vortex tube arrived and found a standard that had no category waiting for a system that needs none. When Winter Storm Uri struck Texas in February 2021 and the power grid collapsed, every vapor compression refrigeration system across the state, in hospitals, blood banks, pharmaceutical facilities, and food storage, stopped the moment grid power was interrupted. The compressed air in every hospital's pneumatic tool system kept pressure in the lines. A vortex tube connected to that system would have kept cooling whatever needed cooling through the entire outage, with no refrigerant charge depleting, no moving parts failing, and no certified technician required in the middle of a statewide emergency. The refrigerant industry spent $22.4 billion last year selling a chemical that requires annual servicing, generates compliance obligations under 3 separate federal regulations, and stops working the moment the compressor that circulates it loses power. NASA decided in the 1960s that a device with no moving parts and no chemical charge was the only acceptable cooling technology for a human life support system. Georges Ranque watched room temperature air separate into a hot stream and a cold stream inside a steel tube in a Saint-Étienne factory in 1930 and spent 3 years trying to explain what he had seen. Rudolf Hilsch confirmed every measurement in 1945. The tube has not changed. The temperature separation still happens. The physics are still running. The question was never whether it works. The question is why we're still asking why we don't use it. This is Off the Meter Subscribe, so you never miss the next solution the world forgot to use.